We have hit a number of milestones for quantum computing in the last couple of years. New chips, new algorithms, error correction, new records. And while all of this is pretty cool, we must never lose sight of the end game here. When we actually get a fully scalable, fully error-correcting quantum computer, which actually useful things can we do with it? Like, what are quantum computers good for? One obvious answer is using Shor's algorithm to defeat current encryption for everything. Emails, credit cards, government data. And yes, that's a big deal, but you will need millions of qubits to pull this off. And there's an even bigger problem. People can just switch to new encryption schemes that cannot be cracked by Shor, because those do exist. So apart from being this NSA toy with expiration date, what else have quantum computers to offer? Well, as Richard Feynman figured out in the 1980s, nothing can simulate a quantum system quite like another quantum system. So let's talk about quantum simulations. Quantum simulations simulate quantum systems. So they allow us to figure out in detail what atoms and molecules do, like activation energies or reaction chains, etc. With this, we can understand chemical processes, for example, nitrogen fixation, which turns dinitrogen into ammonia. Ammonia is the key ingredient for all artificial fertilizers, without which we could not feed 8 billion people. We have found a synthetic process for this called Haber-Bosch, and Veritasium actually made an excellent video about this. But that only works at high temperatures and is extremely energy intensive. In fact, we use 2 to 3% of the total world output in energy just for producing fertilizer. However, there's also a natural enzyme called nitrogenase, which runs nitrogen fixation at ambient temperature. If we could exactly simulate what happens in nitrogenase, and especially in the FeMo-Co cofactor, basically a vital helper molecule, we might be able to reproduce this and run nitrogen fixation without the crazy energy input. Another example is photocatalysis, a chemical process which could potentially break down CO2 just using light and turn it into very useful chemicals, maybe even natural gas. And there are many more possible applications, so quantum simulation could actually lead to improved battery technology, material science, high-temperature superconductors, etc. Alright, sounds great, but how does it work? It's very difficult for computers to simulate what molecules do and how they interact, because they're quantum systems. And the more components a quantum system has, and the stronger the interactions between those components are, the more things you have to calculate. For each added particle, the complexity of a system grows exponentially. The number of quantum states keep doubling, tripling, or even worse. And that's why today, for example, we cannot calculate the behavior of complex molecules, even though we know all the basic rules that apply. But our computers are simply not powerful enough. And that's where quantum computers come in, because they are quantum systems themselves. So when you add more qubits to a quantum computer, they have the same exponential growth, but in power. The same thing that makes quantum systems exponentially harder to solve makes quantum computers exponentially better at solving them. And that makes them uniquely suitable to run quantum simulations. A typical workflow would look like this. We start with the problem definition. To describe the system, we need something called the Hamiltonian. This is a mathematical description of what parts a system consists of and how they interact with each other. For example, this is the Hamiltonian of the Ising model, which is made up just of particles with spin arrayed in a grid. Basically, every spin has two possible states and can flip to change them. The Hamiltonian gives the reaction of each spin to an outside field and also an interaction between next neighbors. This very simplistic model was originally conceived to describe magnetism, but it can also be used to model other things, like mixing in a gas or even neural networks. A Hamiltonian for a chemical process would look very similar to this. In general, we have a sum over a large number of interactions within small areas of the system, similar to the next neighbor interactions in the Ising model. This system description must then be translated to the language of quantum computing. Qubits are much simpler objects than real atoms. They only have two states. Also, the types of operations that can be performed on qubits, the quantum gates, is much more restricted. The properties and behavior of the real system must be encoded to qubits and a quantum circuit. But there are some established methods to do just that, like Jordan-Wigner or Bravi-Kitaev. The next step is the actual computation. Starting from an initial state, we apply the time evolution operator, which is based on a Hamiltonian, to the system and finally get the output state. And this includes the key concept of quantum simulation, which is called Trotterization. Okay, this part will be more technical, but Trotterization really is the most fundamental concept we need to talk about. The general scheme of quantum mechanics is: start from the initial state, apply the time evolution, and this gives you the final state, the result we're interested in. This process is actually the same as solving the Schrödinger equation, the basic equation of quantum mechanics, just written down differently. And we can explicitly solve this for some problems, but not really for any realistically interesting ones. So what we do is what we do with almost any kind of simulation. We break the process down into many small steps and approximate each small step to simplify it. Typically, if we keep the steps small enough, we get a result that is close enough to the exact solution. And this is also true here, thanks to the Trotter formula. Remember that the typical Hamiltonian for chemical systems is a sum of many small, short-range interactions. If you know anything about exponentials, you know there is a nifty formula for the exponentials of sums. And we would very much like to use that. Unfortunately, this rule does not in general apply to quantum operators because they do not commute, meaning you cannot simply switch around the order of operations. Rather, you have the more complicated Baker-Campbell-Hausdorff formula, and this gets really ugly really quick. Thankfully, there is also the Trotter formula that says if you turn the exponential sum into an infinite product of infinitely small exponentials, then the identity holds. So that's what we have to do. Exchange the exponential sum of many Hamiltonians into a product of many small exponentials. Obviously, we cannot do this literally infinite times, but if we do it in many small steps, the result will still be approximately correct. And this whole process is called Trotterization, and most quantum simulations rely on exactly that. The remaining question is, of course, how close are we to quantum computers that can actually run this kind of simulation? For really big problems like simulating nitrogenase, the quantum computer would have to have around 1 million qubits and full error correction. So that's at least 15-20 years away. So unsurprisingly, we will not be able to start off with the big billion-dollar problems. We will have to start with simpler systems and gradually build up capabilities. Google has already demonstrated some kind of early success with their current, relatively modest 100-qubit Willow chip. But the big thing here is that there are a lot of problems for quantum simulation to solve, with potentially huge impacts. I'm Chris, and this is Physics But Awesome. At the moment, I mostly do stuff on quantum computing, quantum mechanics and cosmology, so if you enjoyed this video, subscribe for more.